Hello, and thank you for joining today's presentation in the Richardson RFPD webinar series, A Walk Around the Block. In today's session, Roy Sweda, Applications Engineer for Licap Technologies, discusses how supercapacitors and lithium-ion capacitors offer IoT sensor applications and autonomous low-power energy harvesting and storage source. So without any further delay, let me turn it over to Roy. Roy, go right ahead.
Hello everyone, I'm Roy Sweda, Applications Engineer at Licap Technologies. Today I'll be talking a little bit about Licap ultracapacitors being used as an energy storage system for outdoor IoT remote sensors. I'll be talking a little bit about what ultracapacitors are, some of the terminology surrounding ultracapacitor advantages, IoT remote sensors, outdoor ESS considerations, ultracapacitor sizing, and an example of a power management IC. Also, a recommended Licap ultracapacitor for this particular application. And then finally, ultracapacitor safety. Ultracapacitors have a very large amount of capacitance in a small volume with little weight. The photo above is one of our products that's about the size of a D-alkaline cell, weighs 65 grams, and has 370 farads of capacitance. Ultracaps provide very high power density, and capacitance can be into the thousands of farads. Up to 100 times the stored energy can be held within an ultracap compared to electrolytic capacitors, and they are capable of very rapid charge and discharge, so they really work out well where you need to collect a lot of energy in a very short period of time, like regenerative braking, for example. Energy is stored in an ultracap electrostatically versus electrochemically in batteries. A little bit about ultracapacitor terminology. You can hear these products referred to as ultracapacitor, supercapacitor, or EDLC. EDLC has to do with the construction of ultracapacitors, and it has to do with the layout of the internal components, the electrodes and electrolyte within the cylindrical can or container. So that stands for electric double layer capacitor. ESR is the equivalent series resistance, and that's really the gateway to the internal energy release capability for ultracapacitors. So we typically are involved in very, very low ESRs for ultracapacitors in the very low milliohm to high microohm range. LIB is lithium-ion battery. SLA is sealed lead acid battery. Those two terms will come up a little bit later in the presentation. CCCV is our charge method. It's our preferred way to charge ultracapacitors, and it's the same as with lithium-ion batteries. It's the constant current, constant voltage method, where you start charging and the voltage is preset to the maximum amount, and the current is also set. When the charge reaches the set voltage, the current starts to diminish. And actually, if you leave it charging long enough, you would reach what's called the leakage current for an ultracapacitor. And I'll go into that a little bit more later as well. Common units, F is for capacitance for farad. Voltage is V, current is A, of course, and power in watts, W. Energy is watt hours, and ESR is typically used in milliohms. And then one final note, a joule is 1 watt second. Ultracapacitors have a lot of advantages over other forms of energy storage. For one thing, the cycle life is very long for ultracapacitors, even compared to some of the best lithium-ion batteries. So you can see we've got up to 1 million cycles for cycle life versus maybe maximum of 1,000 for lithium-ion battery. We have a very low ESR. We have a very wide operating charge and discharge temperature range, -40 to +60 degrees C. Typically with lithium-ion batteries, charging is restricted to about 0 to 45 degrees C. So that's quite a difference in the temperature range. We typically can provide close to or 100% stored capacity at minus 40 degrees C. And lithium-ion batteries, for example, may give you at minus 20 degrees, maybe 30% of the stored energy is available. Charging is the same as lithium-ion batteries. As I mentioned before, it's the constant current, constant voltage method. Ultracapacitors are easily stacked and paralleled, so we can adjust for different voltage requirements. And then when we parallel those series stacks, we can also adjust the amount of stored energy available. Low maintenance and replacement costs versus lithium-ion and sealed lead-acid batteries. Just a quick word about Iot Remote Sensors. Some of the applications for these types of sensors include smart infrastructure, smart agriculture, smart city, and in my case that I'll be explaining later, a remote power line monitoring IoT device. These sensors have typically very low power requirements, usually in the tens of milliwatts. These sensors are usually located outdoors, and the energy storage system has to be capable of capturing and providing power over a wide temperature range. So an alternative to power wiring or batteries that need replacing is pretty much an autonomous power harvesting system that uses the ultracapacitors as the ESS or the energy storage component to meet the low power requirements. Many advantages over batteries. At low power, ultracapacitors typically behave more like an energy storage device versus the high power delivery type devices that they're commonly referred to. Some things to think about when you're considering an energy storage system for outdoor applications. You're usually dealing with a very wide operating temperature range. Most specs go down to minus 32 and lower, and with a high limit up around plus 60 degrees C. Charging is usually accomplished in these remote locations with solar cells or photovoltaics as the power generator. The high discharge charge efficiency of ultracaps really lend themselves well to being charged by a solar cell, which may not have much output at times due to conditions, weather conditions. ESS required to cover blackout days, and these are the times when the solar cells are not providing enough power to be doing a charge operation on the ultracapacitors. And the remote locations make battery replacement very impractical and very costly. So if you have to get out somewhere to change a battery or replace one that's worn out, if it's rechargeable, it's going to cost a lot of money. Power management IC selection is also something that needs to be taken into consideration, and I will be covering a little bit more about that a little bit further into the presentation. So some things to think about when you're sizing an energy storage system with ultracapacitors as the primary storage device. So I have here an example of an outdoor power line monitor, and this line monitor needs to run for about 3 days while it's consuming 10 milliwatts of power. So that 3-day period I would consider to be the kind of the standard blackout period, where you could be sitting there for 3 days without any charge current being supplied to the ultracapacitors. So 10 milliwatts times 72 hours is equal to 0.72 watt hours. And then that's the total energy required for running a 10 milliwatt power requirement for 3 days. And then normally for our ultracapacitors, we consider end of life at the point where the ultracapacitors reach 80% of their initial capacitance. So we have to upsize initially to compensate for that end-of-life requirement. So you just divide 0.72 by 0.8 and come up with 0.9 watt hours. And that's the value that I will be using to do the sizing exercise. Also, the charge voltage, charge and discharge voltage range of the power management IC, it ranges from 2.2 volts to 5.2 volts. So the energy storage capacity for ultracapacitors is calculated where the equation is E stored is equal to 1/2 CV squared divided by 3600. And the final result of that equation is in watt hours. And so C is capacitance in farads. V is the operating voltage where it's V max minus V min. And then 350 farad cell maximum voltage is 3 volts. And we need 2 of these cells connected in series to reach or to be able to accommodate the 5.2 volt maximum voltage from the power management IC. Each one of these 2 series ultracapacitor strings stores 0.57 watt hours if you use the equation up above. So if you take the original 0.9 watt hour energy requirement and divide that by the string storage capacity of 0.57, you'll come up with requiring 2 series strings in parallel. So we're looking at 2 ultracapacitors at 370 farads connected in series, and then 2 of those series strings connected in parallel. And the total energy storage capacity is 1.14 watt hours. So the total capacitance for the 2S2P module is 370 farads. The total ESR is 2.4 milliohms, and those numbers are exactly the same as the cell, because when you put 2 cells in series, you divide the capacitance by 2 or multiply the ESR by 2, and then when you add another parallel string, then you do the opposite for the 2 values, and you multiply the capacitance by 2 and then divide the resistance by 2, and you come up with the total capacitance and ESR for the entire module. Here's an example of a power management IC. This one is from Analog Devices. It's their ADP5090. And this device is capable of harvesting power in the microwatt to milliwatt range from a bunch of different sources, including photovoltaics. And this device also has programmable maximum power point tracking, and that's for optimizing the solar generated power to charge ultracapacitors. And then this device keeps the ultracapacitors operating within their proper voltage ranges, and in this case it's acting as a pretty much like a battery pack protection circuit for the ultracapacitors to make sure that they don't go over voltage or under voltage. And in the case of our ultracapacitors, we can go all the way down to 0. So the lower voltage limit typically is dependent on the dropout voltage for the device that we're powering. For our example application, I wanted to recommend a Licap ultracapacitor. It's our model SC0370-300-RSS. And this is our 350 farad ultracapacitor. Rated voltage is 3 volts, and the ESR typically for this model is 2.4 milliohms. And the maximum leakage current is 0.3 3 milliamps. And that leakage current refers to the amount of current that's continuously flowing after you've left the ultracapacitor at full charge voltage for 72 hours. And there's a certain amount of current that is required to maintain at 3 volts. And if you remove that charge current, and it's typically very low, in the very low milliohm range, like 1 milliamp or less. And so if you remove that current supply, then the voltage level of the ultracapacitor is going to start dropping, and we call that the self-discharge rate. So leakage current is kind of the opposite of self-discharge, but they're very interrelated. Usable stored energy for this component is 0.35 watt hours, and when I say usable stored energy, that's using Vmax as 3 volts and Vmin at 1.5, and that's our usual method for specifying our watt-hour storage capacity. We call it the usable stored energy, and it's from Vmax to 0.5 of Vmax. Energy density is 8.86 watt-hours per liter, and the operating temperature range is -40 to +65 degrees C. And the size is, like I said earlier, about the size of a D-alkaline cell, 61 millimeters in length by 33 millimeters in diameter. And then the weight is 65 grams. So finally, last but not least, ultracapacitor safety, and this is very important. So I wanted to remind you that EDLC ultracapacitors are definitely an energy storage device with that low ESR that we talked about, and it's capable of very high rates of discharge. And as such, you have to treat these devices with the utmost respect, especially if you've got a lot of them in series and you're talking, in the hundreds of volt range. You should always consider an ultracapacitor to be fully charged until determined otherwise. So I've seen people put something across an ultracapacitor, and you wouldn't believe the arcing that goes on, or that can happen. Licap products have to always be operated within established datasheet specifications, and we never allow an application or recommend highly against an application that may want to go outside of our established datasheet specifications. Never ever short circuit an ultracapacitor, either cell or modules, which is the combination of cells in series and parallel. And then never connect a module in parallel with another module or a battery without some form of current limiting, unless the voltage levels of each of those are pretty close to equal. Thank you for joining in today. If you would like more information, feel free to contact me directly at the email address or phone number below, or you can check out our website, www.licaptechnologies.com.
Thank you again for today's presentation, and thank you from both Licap Technologies and Richardson RFPD for attending today's session. We look forward to you joining our other sessions in this webinar series. Thank you.